8.2, insertion sort. Now we are ready to do insertion sort. Just putting all the insertion steps together, one by one, one after another. But the main thing we need to do here, analysis. The best case, the worst case, analysis. Yeah. All right. So let us estimate efficiency. Yeah. So we go through the whole insertion sort. At the same time, we estimate the efficiency. All right. Here, we just do the compare and shift operation. So one comparison and one shift operation. All right. So here you can see the basic idea is like this. We lift the current element because when we work on element by element, we assume the current element we are working on, this one, A sub k. So then we lift this. That means we copy this element to a temporary location. After that, then we do compare and shift operation. All right. So that's the procedure we did in the previous video, E.1. Yeah. But here, let's look at the worst case efficiency. For the worst case, we need to do compare and shift all the way to the left end. Okay, that's the worst. Yeah. In that case, the number of compare and shift operation we need to do 1 plus 2 plus 3. And the last one, n minus 1. The first one compare and shift operation, right? So then after that, one more than the previous one, and so on. Yeah. So this we get 1/2 times n minus 1. Now, if we use the asymptotic notation, that is big theta of n squared. Yeah. Then the best case. Yeah. So we can see for the best case efficiency, when we do the first compare and shift operation, we get it. Or the current element AK is greater than A sub k minus 1, then we just put AK in place. We just put AK in place. Okay? Yeah. So you can see each insertion, we only need to do one compare and shift operation. Or let's say one comparison, because we do not even need to do shift operation, right? One comparison. Then, put the current element in place. Or we can modify our algorithm a little bit. We do not even need to move AK out, right? Yeah, we can modify our element. We do not even need to move AK out. Yeah. So that simple adjustment should be very easy. Yeah, here I do not need to get into that kind of details. Yeah. Anyway, so the answer will be n minus 1 comparisons. The best case, n minus 1 comparisons. If we use the asymptotic notation, that is just big theta of n. Yeah. So here you can see the difference is big. The best case, the worst case, the difference is big. Okay? Yeah. Another one, the average case. The average case, for each insertion, we need to get the average number of comparisons. Okay? Then we add them together. Here I do not do it explicitly. You can try if you like it. Yeah. But you will see the answer will be still big theta of n squared. Big theta of n squared. Yeah. Actually, approximately 1/2 of the worst case. 1/2 of the worst case. Average, somewhere in the middle, right? So 1/2, yeah. Naturally, you multiply the worst case by 1/2, you get average case, but that's the approximate number. Yeah, it's good enough. It's a pretty good approximation. Yeah. All right. Yeah. How to derive it? Yeah. So you use this idea. So do some careful computation. You can get it. Yeah. So we can skip that part. Yeah. But here, this property is very nice. So what property? The best case efficiency is very good. You can see if you look at other sorting algorithm, it is rare to find an algorithm with this property. It is rare to get an algorithm whose best case has this efficiency. It is very rare. Yeah. So you can see from this point of view, insertion sort is very special. Yeah. Here, I like to point out a special application of that property. Yeah. So as a conclusion, so we can say in this way. Yeah. If the given array is almost sorted. So what do you mean almost sorted? Yeah. I will use a diagram to show you the meaning. So you can get an idea a little bit, almost sorted. Yeah. So then the insertion sort is a good choice of sorting. Good choice. Yeah. Here in this diagram, suppose this line segment represents the whole array. Yeah. We assume it is almost sorted. Yeah. Then only some small number of scattered locations, locally, there are a few elements that are not in order. Okay, so here I use red circle to represent. So these are few places, not too many, a small number of locations that, a small number of elements there are not in order. Yeah. If your data has this property, then the best sorting algorithm to make it sorted is the insertion sort. Yeah. But the data with this property is very rare, so not very common. Yeah. But in case you happen to have this kind of data, definitely insertion sort is the best choice. Yeah. All right, so here we complete the insertion sort. We complete the discussion of the insertion sort. Yeah. But the next, I like to do some simple applications of the insertion sort. Insertion sort, the idea is very simple, but it is very useful. So here I want to show you some examples how useful it is, especially the idea. How useful is this idea, the thinking way? Yeah. All right. Let me just use some simple example. All right. Insertion with binary search. Here, let me explain this idea. So let's recall our typical insertion step. Yeah. So we have an array. All this array already in order. Ordered array. Okay? Ordered array. All right? Yeah. When we insert a new element into it, because we need to do compare and shift operation, right? Compare and shift operation. So that's why we need to go from the very end from the right? So then one after another one, right? Yeah. Here the reason is because we need to make our shifting operation as easy as possible. That's why we work from one end, right? Yeah, one end, all right? Yeah. But here, we want to modify this step a little bit. Modify the step a little bit. Yeah. All right. Because the first step, remember, we need to do two steps. The first step, find the right location, right position of the current element. Second, insert it. Insert the current element at the right location. Here, we just look at the first step. Find the right position. Only this step. In the ordered array. Remember, find the right position in the ordered array. When you do it in the ordered array, what is the best way to do it? Binary search. The fastest way to do it, find the right location. That is the binary search, not sequential search. Yeah. But in our standard insertion sort, the reason we do the sequential search, we want to consider the shifting operation. Okay? This is, the reason we do the standard insertion operation, because we need to make the shift operation as easy as possible. That's the reason. Yeah. All right. In other words, if we want to take advantage of the efficiency of the binary search, then we have to avoid shift operation. If we cannot avoid shift operation, then you cannot use this binary search way to find the right location. That is the new view of it. New view. Here, I want to use this new view to solve a few problems. So let you see how important is this insertion idea. Okay? All right. Yeah. Remember, here I want to talk about our midterm question. Midterm. Midterm question, the last one, number 25. Sort 4-element array. Sort 4-element array. Do you still remember how well you did in that question? Based on my statistics, the error rate, the miss rate or error rate, 50%. One half of the class couldn't get it correct. Yeah. The other half, although they gave the correct answer, but I don't know if they know how to solve it or not. Because this question, I only ask you to put the correct answer. So those students just put the correct answer 5. They didn't give me the details. Yeah. So I don't know if they can solve it in the correct way or not. If I ask you solution, remember, if I ask you to put a solution, because if you see the solution, you should give me the details. If I change that question to solution, I believe this number will be reduced to, the error rate will be increased to a much higher number. 75%, 80%, or even 90%. Could be very high. Yeah. But here, let me use our new insertion idea to solve that problem. Okay? So we will use the new insertion idea to solve it. New insertion idea. Although there are many ways to solve it, but using this insertion idea, it is very interesting. Okay? All right, so let me show you. Yeah. All right, special sorting problem. Sorting 4-element array, it's a special one. Okay, the reason this insertion idea is good for special sorting problem, usually the size is small. The problem size is small. When the size is big, so this idea may not be very good. The reason is we cannot do it, in a well-organized way. For the small size, then we can handle that easily. Yeah. All right. So let me start with a 3-element array. Three-element array. That's simple, but we have to go through it. From 3-element array, then move to 4-element array. We have to do step by step. So for that reason, we need to start with 3-element array. To solve 3-element array, we need 3 comparisons, right? Here, I just use the insertion idea to do it. 3-element array, okay? All right. First, let's say we have x1, x2. To get x1, x2 sorted, we need 1 comparison, right? 1 comparison to get it sorted. All right? Then x3. Now we use the insertion idea. Okay? All right. The insertion idea you compare with x2 first. Less than, greater than, right? Greater than x2, you already get it sorted. But that's not the worst case. So now we need to consider the worst case. Worst case, we assume x3 less than x2. So we need another comparison. Then 2 more comparison. Okay? 2 more comparison. 1 plus 2, 3. 3 comparison. Okay? All right? Okay? All right. Continuation. Yeah. Continuation. Here we use 3 comparisons to get 3-element array sorted. x1, x2, x3, right? Yeah. Now the 4th element. Now our 4-element array sorting problem. Okay? We want to see how many more comparisons we need on top of this 3. We already spent 3 comparisons to get the first 3 elements sorted. Next, we need to put the last element in place. And we want to use the minimum number of comparisons. How many do we need? Yeah. Now, insertion idea. Okay? Insertion with binary search version, not the sequential search version. Binary search, because we do not need to worry about the shift operation, right? Because for the small problem size, we can do manipulations, explicitly, manually, right? So we don't worry about the shift operation. Yeah. All right. So now, in order to find the right location, binary search, not sequential search. Yeah. Compare x4 with the one in the middle. Binary search, you always compare current element with the element in the middle. Okay. So that's the first comparison, right? Yeah. So it could be greater than x2 or less than x2. If it's greater than x2, then the next one you compare x3. Another comparison, your second comparison, right? Then you find the right position, right? No matter it is greater than x3 or less than x3, you get the whole array sorted. If it is less than x2, your second comparison should be with the first one. Yeah. That means after 2 more comparisons, you get the array sorted. Yeah. So at the end, the number comparison 3 plus 2. 3 to get the first 3 elements sorted, plus 2 to put the last element in place. The total 5 comparisons. Can you do it in this way? So in our midterm, you do not, because we didn't learn insertion sort in the midterm, but you can work on it manually, right? Manually. Remember, when I post my answer sheet for the midterm, I use handwriting. So on our test paper, I use handwriting to write the answers, comparison details. In that place, I didn't use insertion sort. I didn't use insertion idea. That means you can still do it without insertion sort background. You can still do it. Yeah. But here, the reason I introduced this insertion with binary search idea, because it is very useful. It is very interesting. Okay? Yeah. All right. The last thing, before I finish this video, the last thing I want to get to you, the question. So this is a very challenging question, and we will do it in our video number 3. E.3, we will do it. How to sort five element array. Okay. All right. Yeah. Oh, by the way, just a few more sentences before we finish this one. Oh, I saw many students, they give me the correct answer because they found the formula. They searched the web and found the formula. The minimum number comparisons to sort n element array, they found it on web. That is ceiling function of natural log of n factorial ceiling function. They find this one. They plug in 4 elements, right? 4. And when they calculate 4 factorial, 24 ceiling function, they get 5. Yeah, I saw quite some students. They just plug in the formula. That means they may not know how to really sort these 4 elements using 5 comparisons. They may not know it. Okay, all right, so that's the last few sentences. All right, let me finish right here. Yeah.